So here's a second version of our specification, actually. It's the second version of the specification in TLA+. That's a specification of this. The comment is wrong here, actually. Okay. I did synchronization the wrong way yesterday. So that's a specification of fast sync where we try to focus on the reactor side and the FSM side. So we don't talk about how the FSM is communicating with the peers. That's all the reactor's job, right? We only receive events from the reactor and we issue some, FSM also issues some events to the reactor back. And we also try to minimize the number of timeout events in the spec because it's a bit too hard to reason about timeouts in TLA. Okay, let's start. That's like a typical TLA spec. This one is a bit too long in comparison to standard examples. So what we have here, we use the integers module and finite sets module, right? So we are going to talk about integers and finite sets. There are a few input parameters here. That's a set of peer IDs. So that's not important who your peers are, just you know the IDs, right? You can imagine this were public keys or something like that. But in this example, this will be just, in this case, these are just numbers, 0, 1, 2, and so on. Then you have the ultimate height. That's the maximum height you can reach in the blockchain, you know, at all. So it's like an upper bound on the height that just we need it for modeling. You can imagine that the peers are having some, they progressed at some to some height, right? But they never progress beyond the ultimate height, right? Then we have the number of requests. That's how many requests each peer will, the FSM will produce at a time. For instance, 2 requests, in reality it's 20, right? So these are constants that you give to the specification. And typically you would pick small constants to do model checking, right? So people are disappearing, huh? Do you hear me?
Yeah.
Okay, good. So then we have a few definitions. These are real like standard ones. Usually have some standard definitions. Usually we have a value for something like a null value. It's usually called none in TLA, but it's just a definition for something you use as a null, right? In this case, it's -1. Then there is a set of heights, right, that we will use. That's basically a set from 1, 2, 3, and so on until the ultimate height, right? Here are 2 very simple operator definitions of minimum and maximum, right? That's how you start learning TLA. You define these things. And then we have our variables. So these are the things that are changing during an execution, right? So first of all, there is a turn, which tells us who's making the step. It's either the FSM or the reactor. We only have 2 entities here, the FSM and the reactor. Then the reactor is producing in events for the FSM, and there is also a variable which is telling us whether the reactor is running or not. Then the FSM, it has an internal state which is very much like the state as in the implementation. It consumes the input events from the reactor, and it produces output events to the reactor, right? Are you with me?
Yep.
Good.
I am.
Okay.
Yeah.
So these are just variables, okay? There are no types because in TLA you don't have any types. But we'll see how these variables are used in the actual specification, right? And finally, the most important thing here is the block pool. That's a record that tells us how far we have made it in the fast sync process, right? So that you have the height, which is telling you that if you're at height, say 10, it means that you have to receive a block for the height 10, right? This is a set of peers you have heard from. So these are the peers who responded to you and gave you a status update, right? And for each peer in this set of peers, you actually know the height that this peer has now, right? From the last update. So you have this mapping from peer ID to the height, and that's just a function. You can imagine it's an array. Then you have the max peer height, which is the maximal height you have seen among the peers, right? Then you have the blocks that tell you for each height which peer has been assigned to which block. Then you have the next request height, which tells you from which height you are going to start the requests, right? You have the received blocks, which tell you for which heights you have received the blocks, right? And finally, you have the processed heights, which tell you for which heights you have received the block and processed it successfully, okay? So here you see it's all in the comments, right? Because TLA doesn't have types. But you will see when I define the block pool in the initial state and when I define the progress of the block pool, you will see that all these fields will appear in the expressions.
So a question here, so in TLA, you can't even define a structure, or when you say there are no types, it means there are even no structures.
You can define a structure. It just it's like Python, you know.
Okay.
So when you want to say that block pool equals to something like here,
okay,
right? You actually define a structure. It's a record, right?
Okay.
But you don't fix the type of each variable, you know?
Okay.
So it can actually change with the execution. In Appalachia, we change it because we actually have a static type system. But in TLA in general, it's like in Python. So you can imagine you have dynamic types, right?
In Pascal, it's the same, I guess.
Yeah, Pascal is translated to TLA, so they have exactly the same thing here. So yeah, the most important thing here is this data structure. And this data structure is almost like the data structure that you would see in the implementation, except these two guys. These two guys are like additional variables that we need in the protocol to specify its behavior, to specify what kind of properties it has, and to reason about what things we have received so far, to specify what the reactor is able to do. Okay?
Mm-hmm.
So then there are really like a bunch of definitions. We actually can skip all of them. I just want to give you this feeling of how, you know, you would write a TLA spec if you want to, to make it understandable more or less. So then there is a set of states. These are exactly the states that you have in the implementation, right? So the FSM can be in one of these four states: init, wait for peer, wait for block, and finish. Right? Then this is interesting. So we have a set of blocks that you would receive from the peers. And here you should start shouting because this is a set of blocks, right? It tells us that the set of blocks is exactly the set of two records where valid is equal to false and where valid is equal to true. Okay? So from the perspective of this protocol, you don't care what's inside the blocks. You only care about whether you have received a valid block or not.
Why is it a colon and not an arrow here?
So this Hank is telling you that it's a set actually. It's a set that it's a set of records. We could have written it differently, right? We could have written it like this. B in Boolean.
But couldn't
no.
you
No.
have written
like this? Yeah.
Okay. And how is that different from writing just valid arrow Boolean?
Valid. Oh, that would be different. Because here you define a set of records. And if you would write valid arrow Boolean, that would be a single record.
No, without the bar.
Like this?
That's the function, yeah.
Okay. Well, first of all, this is not.
It's not a valid syntax.
Yeah, I'm not sure what you want to define here.
Have this. Can you scroll up a bit? Sorry.
Yeah.
Like peer heights.
Yeah, but look. Yeah.
Like
this one. I see. So in the TLA syntax, you actually, if you read the book carefully, right, you will see that a record is actually a function like this record, right?
Mm.
So a record is actually a function that for the string value valid will return you a Boolean value, right?
Mm-hmm.
And then if you look at the more complex record, for instance, here's a set of records, right? Here's a set of records that have type, peer ID, and height. Actually, it's a set of functions that return you for type, it will return you this value, status response event. For peer ID, for the string peer ID, it will return you one of the values from here. And for the string height, it will return you one of the heights from here. Okay?
Mm-hmm.
So it's a very good question. In TLA, everything is either a set or a function or an integer or a Boolean. I would say it like this. Or, yeah, even sequences are functions. So most of the things that are not sets and not integers and not Booleans are actually functions. Okay?
Okay.
So, I mean, feel free to ask questions because, I mean, it's a completely different language, right?
Mm-hmm.
So if you just don't, if you just don't understand these things, just ask, okay?
So just to be clear, blocks is a set of records where each record has a field valid that is either true or false.
Exactly. So we could have written it this way. Valid false and valid true.
Yeah, I think in one of the Leslie's talks, I think he mentioned that if you use this notation with like for a function essentially where you use this arrow notation, that this is when if you have a kind of a single value, and if you use the column, then it's if you have a sort of the space of values. Or so in this case, if you would be having only you want to have going from valid to either false or true, then you would write it as a function. But if you use column, then you are defining the a set of the values.
Exactly.
What space on the right is I guess I was not really explaining this well, but
yeah, I guess
you are not saying in this case you don't want to say that the result space is Boolean, but you want to say is that actually this is like you want all the elements from that space to be part of the set.
Yes, but I mean there is a relation between the types and the sets here, right? Because you could also read it like all blocks I have should have this shape, right? They're actually structures who have the field name valid, and this field is Boolean, right? So a type is actually a set of values that you can have defined by this type. So I mean, yeah. But maybe this is like the most confusing thing here, because you're not only talking about individual values, you can also talk about sets of values, right? And in TLA, you use sets like just everywhere. Okay?
Sure.
So, yeah. So, okay, the another thing is that here just define the types the events can have, and these are all all the types of the input events. This exactly.
Yeah. Sorry, because I think we have a good example here for invalid block to understand the difference between blocks and invalid block.
Oh yes, yes.
So invalid block is its operator, which returns just false, I guess, or
no, it's a record.
Well, okay. Consider this one as a macro, like in C, right? As a macro that would give you this value, and this value is a record that maps valid to false.
Okay.
And so it's a constant, right? It's a constant record. Usually, if you have an operator definition that doesn't have arguments, it means you define a constant.
Right.
Okay.
Right.
We could also define valid block to map valid to true, and then we could say blocks is the union of invalid block and valid block.
That's also true. There is a lot of flexibility here. You're right. Yeah. You could write it like this. Yeah. Valid block and valid block. Yeah. Yes. So you could do that as well. And yeah, the important thing here that I don't care what's inside the blocks, except the fact that they can be either valid or invalid, right? So then you have the types of the input events, and that's just a set, right? It's a collection of input types. Here, that's probably interesting. That's all kind of input events FSM can receive. And what happens here, you just take these records, right? Each of these guys is a set of records. In this case, it's a set of records where these are actually two records, right? One of them is having type equal to start FSM if, and the other one is having type equal to stop FSM if, right? Have you followed me here?
Yeah.
Good. So that's a set. Then we define another set of records. These guys are having type equal to this guy. And peer ID is always in this set. And the height is always in this set, right? Mm-hmm. So these are other events you can get here. You just take a union of all of them, right? And these are all possible events you can receive as your input if you're FSM, right? So this thing is a bit advanced, right? So this one is telling you that you take a set of all subsets of this set, okay? Except the empty set. So if you have, say, peer IDs equal to 1, 2, and 3, right? Then you would have subset of peer IDs equal to these sets.
Like all sets.
All power set.
Oh, yeah, it's a power set, exactly. And then, yeah, 1, 2, yeah. You see it.
exclude the empty set.
Exactly, because you don't want to remove an empty set of peers, right? It just doesn't make any sense. Good. So these are types of events that the FSM can issue to the reactor. This is something new. You don't have it in the implementation, right? It just says I issue no event. And the other ones are like in the implementation. So you can have status requests, block requests, peer errors. I guess we're not using this one, but in principle, it does exist. And switch to consensus, okay? And like with input events, you have a set of output events, okay? Good. So, and here's an example of no event, right? It's just a record that has the type no event and nothing else.
Can we do a quick poll at this point? Like, are people able to read this? Like, if the spec we would write this way, like, how many people would object at this point in time that this is something not readable?
No, it's readable. I think it's cool.
Wow, I'm impressed because the first time I saw TLA, I was like saying, "What the shit?"
Yeah, look, it is weird compared to other languages, but it's.
Why doesn't it just use like algebraic data types or something?
Well, I mean, you're asking whether you can use them or not?
Yeah.
Well, you can have records. It's a good question. I mean, you can have records that kind of emulate algebraic data types, right?
Well, that's what we're doing here, basically, right?
Yeah, yeah. It doesn't look as nice as it would look in Scala or Rust, I would say, right? When they're talking about algebraic data types. But there are other good things. Usually you use sets, functions, tuples, and the records, right? Yeah, somehow, yeah, if Leslie knew more about, say, Scala or Haskell, he would stuff.
I'm not sure. I mean, he always says he wants it to be like mathematics and
yeah.
So, but
yeah.
basically we're looking at like an enum. Both of these are enums basically, right? You can imagine mapping this pretty clearly to a enum definition in Rust.
Which ones? I mean, these ones, yeah?
Yeah.
Yeah.
Well, and the one below, right? The in events.
Mm-hmm.
Yeah.
Well, it's more like, these ones are more like unions in C.
Right.
That's the thing, right? Because you actually take a union of all of these guys, and then when you retrieve one of these guys from a set, you actually have to look into the type.
Right.
So that's a weird thing. I mean, I guess Leslie was designing these things coming from C, and I don't know.
But still, like, if you think about like the specification of the protocol, this is good enough. Like, you understand what are the. You can imagine also if we talk about messages we exchange, that messages are, we mentioned what are important fields, and we don't necessarily at a spec level need to say what is really type of it.
Yeah. I mean, it's a good point. That's actually how you usually specify messages. In this case, it's events, but that's exactly how you would write messages as well. Good. So I'm going to skip all of these definitions because I don't want to scare you for now. Okay. I will show you a very nice definition of the reactor. So actually this is a complete definition of a chaotic reactor. What it does, initially it produces the event which starts the finite state machine. It starts to run itself, right? And then at any point in time, it can get a value from Boolean, which means it can stop at any point in time. And if it's running, it produces just an arbitrary event from the set of events you have seen, or nothing, if it's not running. So, do you like this one?
How does it know that the next event is arbitrary? If you don't specify, so like line 217 over there, how do you know that Is it like a default in TLA Plus that if you tell it to produce an event from that set, that it'll pick an arbitrary one?
So this is a formula that tells you how the next state of your execution.
So it's basically a constraint, right?
It's a constraint, exactly.
That makes sense.
Not like
Cool.
a declarative or imperative. Sorry, it's not an imperative program.
Yeah.
Exactly. Very good. Very good. Very good. So basically, this one is telling you that the next value in the next state, the next value of in event, just belongs to this set, and you don't specify any other constraint. You can introduce more constraints, but you don't, right? In this case.
But when you write this, the TLC will generate behavior for every possible case here. So
Exactly. Exactly.
It's actually not true that it's random. It's actually for all options there. But is this something which is like TLC specific thing, or it already belongs to TLA, the language itself?
No. This is a perfect TLA constraint. It's just typically in TLC you would write things like this, that look more or less like assignments, So what you usually do in TLC, you would write something that looks like an assignment and then add a bit of constraints on the side just to, to restrict this event prime further,
So with TLA Plus, we actually modeled the logic or some protocol by specifying what are the valid transition states.
Yes.
And that's all we do. We just say these are the possible, and then like when we want to check something, then we just use the all possible space of behaviors and try to see if invariance doesn't hold or hold.
Yes. So what TLC would do, it will just try to produce all possible next states for the reactor. It will try to enumerate all possible values for these two variables so that they satisfy this constraint. Okay? I mean, it's a bit more smarter than what I'm saying, but you can imagine it like that. So TLC just keeps enumerating values for reactor running prime and in event prime in events. Whatever satisfies this formula can be the next state of the execution here. Whatever doesn't satisfy this formula, it throws it away. Okay? And then it keeps unrolling, it keeps producing new states, it keeps unrolling these executions, So actually it collects all the states it could reach, within like 10 steps and then goes to step 11. You see? So instead of saying what exactly you should do in your specification, like in a program, you just say how states can look like. And that's a very powerful idea. That's really, you don't tell what you want to do, you tell how you want things done, how you want things to look like, actually, right?
So, but one thing is that so if you talk about producing events, it's a little bit cheating, no? You're not like filling a pipeline with events and someone's taking it. It's just one, you overwrite the previous one, right? If
yes.
you restrict sort of the strict way in which they alternate, you might lose events.
Very good. So since you understand this part, I will go to another part where I will show you how I combine the reactor and FSM. So let's not talk about FSM now because it's complicated, but this is the composition of the FSM and the reactor, right? So initially you say that it's FSM's turn and you initialize the reactor and the FSM. Then at each step you flip the turn, right? So if it's FSM now, then it will be reactor. Otherwise it's FSM. And if it's the turn of the finite state machine, you say apply these constraints that FSM has and reset the input events to nothing, right? Because FSM doesn't produce input events. And keep reactor running if it was running. And if it's a reactor step, then you produce the events as you have seen before, for instance. by applying this next reactor definition, and you produce no output events because that's what FSM should do. And you don't change the internal state of the FSM. Okay? So that's actually the composition of these two. So they always alternate in FSM reactor, FSM reactor, FSM reactor, and so on and so forth.
What is state again?
So the state is the state of the finite state machine, right? It's one of these guys like wait for block, wait for peer, init, and finish.
Yeah, right.
Yeah. So that's the composition, right? And here you don't have any notions of processes, you don't have any parallel composition, it just, these are constraints, okay? You just say either this guy does a step or this guy does a step, right? So are we good with this one?
Yeah.
So it's a bit tricky here. Initially, actually, initially I wrote a spec like this by saying that the next step is done together by the reactor and by the FSM, which would be just synchronous composition of these two, okay? And it produces a much larger state space. That's why I actually do this way now, because it doesn't change the semantics, but it makes the problem much simpler for the model checker. Okay. So now I can show you the real reactor, not the one that is cheating, you know. So I mean, initially when I wrote the spec, Anka and I, we looked at this stuff, and then Anka said, nah, come on, the reactor cannot do these crazy things all the time, you know? Right?
Sure.
So then we said, and I kind of tried to specify the reactor which is more honest in the sense of what the actual reactor is doing. So the actual reactor is working like this. Okay, if it's not running and it's producing no events, right? Otherwise, it can execute one of these 8 actions. It can send a block request, and that's like a periodic event, right? It can produce a status response from a peer. It can produce a block response. It can remove a peer. It can react to a peer error. It can produce this event on process received block. That's also happening periodically. Then it can stop synchronization, and it can have a global timeout, okay? So this link is telling you that one of these formulas should hold true, which you can understand as pick one of these actions, okay? So it's basically pick whatever action you like as soon as the constraints of this action are satisfied.
Mm-hmm. But it's really, like, mathematically, it means at least one, right?
Yes, mathematically it means at least one, yes.
So does the model checker have to worry about, like, testing that it's not just one of them, but like any combination of them?
So if none of them holds true, you will have a deadlock.
Mm-hmm.
And the model checker will tell you you have a deadlock.
Mm-hmm.
If more than one holds true, it's the model checker actually will split the search into several combinations. Okay.
Okay.
So essentially, it will know that you are trying to assign values to some variables inside of these actions. And then it will say, let's explore these things one by one. Okay? So it's like really a parallel combination here. Then, but from the mathematical point of view, it's just a formula, as Leslie would tell you. So then let's.
But if you don't write the specification carefully, in principle, you could also like execute 2 of these events, right?
At the same time?
Yeah.
Well, TLC wouldn't do that, but mathematically speaking, yes.
Mhm.
So in real mathematics, yes. In TLC, no. Because TLC is smart enough to understand this actually 2 separate actions, you know, that it should explore independently.
Igor, sorry if
Yeah, sure.
so something. So essentially, here we are describing sort of all possible behaviors. But when we think about the state machine, we are more thinking, or one way of thinking about this is that given a state, we are willing to accept only particular set of events to produce a meaningful output. Otherwise, we'll just drop them. Is there a way to sort of reason this way? Because this might scope the things a bit better, and maybe it makes work of TLC easier. So you don't need to think about all interleavings and all possible scenarios, but just that, you know, given a state,
Yeah.
I can process particular kinds of events.
Oh, yeah, that's what we are doing here, right? We restrict these events further.
Okay.
But
This was one discussion that we also had with Anka at the beginning, to understand whether you should check whether the events that you get are actually consistent, whether you work on the assumption that your reactor is correct,
Mm-hmm.
or
exactly.
whether sort of you only want to verify that everything works fine if the reactor is correct.
Okay.
Yes, so there is always this interplay, right? We started with a chaotic reactor, and then it would produce really like crazy behaviors, where it would stop the machine, start the machine, stop the machine, start the machine, and well, it's not realistic, right? And this reactor is more realistic in the sense of what kind of events it's producing. So for instance, this one, right? It will generate an event that tells the FSM to produce requests to the peer, right?
Mm-hmm.
In the real implementation, of course, you have a timeout, right? Because it's like, it's a ticker, right? Something that, you know, happens like every 10 milliseconds. In TLA, you don't have time, right? So we just say it's an action that can occur anytime. And there are some constraints when it can actually happen, right? First of all, the FSM should be in this state. It should wait for block. And second, there must be some, it shouldn't happen that all requests that you have issued so far are unprocessed, right? So there must be some room for issuing new requests, okay?
And in terms of concurrency, because like all those or some of those rules are touching maybe the same state. Do we assume that they are kind of atomically tried, each of them, and then only one of them will trigger?
Yes. So there is no notion of, you know, overrides in somebody else's memory here. You just make a step, right? And whatever holds before making a step, you just look at whatever holds before making the step and tell how the next stage should look like. So
but we have a lot of like for a given state, we have a lot of those things which could trigger, and so like TLC will generate all possible.
Exactly. So if you have different combinations, right? If you can trigger one of these events, it will try to explore all possible combinations of the events. That's why it explodes like crazy, right? It just has to try all this stuff.
And so what is like the practical way to try to train this that it still somehow reflects, or you can still get a meaningful output from TLC, but still don't because probably we could somehow say, you know, some of those scenarios are not very interesting or doesn't make sense. but does this require constraining it a bit more at the level of the model, or it's probably the best we can do?
Well, you can, when you check some specifications, when you check some properties, you can add additional constraints, you know, to say I'm going to focus on these particular events. I can show you actually. It's pretty much advanced TLA here, so I don't want to scare you here, right? But let's see.
Maybe just do the good termination.
Exactly. So for instance, don't look at the other things here, they're a bit complicated, but for instance, you can say that I assume that my computation doesn't have global timeouts, ever, right? Which means that the input event can never be equal to stop FSM event.
Mm-hmm.
So this already restricts your execution space, and that helps the model checker to, you know, to think about fewer things, right?
Okay.
But yeah, I mean, it's somehow well, it comes with practice. You should, you know, play a lot with the tool, and then you start to understand how you can cut the execution space and the state space into smaller chunks, right?
Mm-hmm.
Usually you would do some abstraction. You would just say, I don't care about these particular data structures, I'll just throw them away. Or instead of saying that I reason about a concrete value of a variable, I reason only about abstract values, like is it below 0 or above 0, or it's actually 0. So there are many tricks to make it smaller.
Yeah, one thing which is kind of interesting for me here is that if you model it this way, you probably are giving a model checker chance to mention you some behaviors or some interleavings you maybe haven't been thought about in general, because we tend to constrain or to scope stuff when we engineer stuff, and just focusing very much on good case.
Exactly.
And like we don't really think like it's not like that there is a small chance that something will not happen. It's more like it will not happen. You just focus on, given a state, I get this message, I get that one, and that's it. And then if something starts for any reason to happen differently, then we normally have problem in the code. So
yeah, I mean, the model checker, I mean, it's quite stupid about what kind of behaviors it explores, right? So, I mean, when Anka and I were debugging this stuff, the examples we got were totally crazy. And that's a good thing, right? Because I also had to refine the spec. I also had bugs in the spec. But yeah, you just get some crazy counterexamples and you never think about them, actually. Okay, so how shall we proceed? I can show you. Do I understand these things, like in general, without, you know, understanding a single piece, every single piece of it?
can you maybe just go in details with one of them, just as an example?
Okay. So, I mean, these things are very stupid, but maybe we'll look at this one. So, this is an interesting thing. In the reactor, you can send the event that an event that the block has been processed, right? This one. So you internally do some verification, I guess, of the block, and then you say it has been processed. And actually, you don't send a processed block event arbitrarily. You actually want to send a block event for the current height of the state machine, right? And only in the case when you have received the block for the height +1. Okay?
Mm-hmm.
So what I write here, let's define this h to be equal to the height of the pool. Then I make sure that I know what to do about the blocks in the block pool. So I have some record about them. Then I know that for the block at height h, there has been a peer who was assigned this block, right? And I know that I have actually received this block for the height h. And the same I do for the h+1, okay? So it kind of, these are like conditions for a successful verification of the block. It's not an exact verification how you would do in the actual implementation, right? But these are like necessary conditions for issuing this event. Are you with me?
Yeah.
Good. So as soon as these constraints hold true, you can produce an input event like this, okay? And as you see here, I say error has a value from the set boolean, which means that although I say I have processed the block, I actually can say that there was an error in the block. So this event, this action can produce two kinds of events. The first one, I have processed the block and it's correct, and I have processed the block and it's actually invalid. Okay? And that's what the FSM will receive as its input event.
And what about, but the blocks that are in there are already deemed to be either valid or invalid. So
What do you mean?
Like,
That's present or not present.
present or not present.
So you have received them, right? But you haven't verified them.
But the definition, so where does that definition we were looking at before about a block is either valid or invalid, where does that?
Well, that is just telling you the scope of all blocks you can have, right?
Yeah.
But is this something which, like, can you show us the logic where when you receive a block, what you do with it?
Yeah.
In the FSM.
Yes.
Okay. Okay. Let's go to the FSM then. Yes.
Yeah, because I guess the reactor is actually received the block, and then now he's sending us event about that block. I guess this is how it works.
So let's see. So first you receive a response from a peer, right? That is telling you that it has a block. But for some height, I guess, right? Yeah, for some height. Then you check whether this block is valid. So if it's invalid or its height doesn't belong to the height you asked for, or if the peer who has sent this block hasn't been assigned this block by the FSM, or if this peer is not known to be your good peer, right? So if it has been evicted at some point, you say I reject it, right? I reject this block and I remove the peer because it seems to be a faulty one. And then I tell the reactor he's a peer error, you should process it. If it's an okay block, then I say, yeah, nothing happened. I mean, we could produce another event, but in this case, nothing happened, right? And I record that I have received this block for this height. Okay, so I only record that I have received the block for this height, not the contents of the block, because I don't care about the contents, right?
Right.
I think there was a small confusion because that invalid block, it's never used really, that macro. So in fact, valid equals false is when we haven't received the block, right? And it's true if we have received the block. We don't know yet if it's valid or not. It's just if we received it or not. In the block pool, I'm saying.
You mean this? Do you mean this field or?
Yeah, the valid field. There is just a presence.
Yeah, I don't know what actually it means. I guess in implementation you also had this flag, right?
Right. So it's the same as the implementation.
Yeah.
But you're talking different things here. I'm not sure I understand, Anka. So at the level of the block pool, you have information whether it's present or not. But when you receive event, the event as part of event, you have you qualify the block as being valid or not. So I assume that validation.
That's the next process block that actually tells us if a block is valid or not.
But is this like in event.block.valid? This is what tells us whether the block validation fails or not.
No, this just tells us if we have received a block or not.
Yeah, I guess this valid doesn't refer to the validation when you take the height and the next height, right?
No, but
So
there's.
I don't know if you remember how this version of fasting works, but we don't do any validation in the FSM. So we ask for blocks, we receive blocks, and we might get an event that says block at height H is invalid or block at height H is valid. In either case, we will then remove the block and we either remove the peer if it was invalid and so on. We don't do the validation inside the FSM.
Okay.
But
the reactor actually does validation, right? And that's what I showed you before.
Exactly. That it pretends it does some validation, so it generates.
Yeah. So here it looks for the conditions where it could do validation, and then it says either the block was actually good or not, valid or not, right? Valid or invalid.
But where does the field, the valid field, get set?
So there is this valid field which is set for I think it was block response. Yeah. So in the block response, you get a block from a set of blocks, right? And exactly, and the set of blocks is defined as this, right?
Yeah.
But I guess the confusion here is that valid is not, doesn't mean exactly the block validation, right? So there are several steps. First you receive a block response, right? That the peer has this block, and this block can be corrupt or not. I don't know what's the right word. That's what is called valid, right? But then the reactor will check, will actually validate the block, and then it will issue this processed block event. And there it will tell you whether the block was actually valid or not.
Yeah, I think Ethan spotted some problem there because it's a bit weird because that we set the valid in the reactor, right? Where do we set the valid actually? Because I don't see it.
So on block response means we received a block from a peer.
Yes.
And it might be valid, it might be invalid, we don't know yet.
Yeah, I guess it's just the name of this field is confusing, right? It does not mean valid from the validation point of view. I guess it means something else.
So that's where the confusion is, that we don't know what valid means.
But we do check it. I thought it means we have received it, but I was wrong. Sorry. So discard my explanation there. But who sets it? Can we go line 522 there? I'm wondering.
What?
522. That's the only other occurrence of valid. Oh, actually, it's 524 because you have a different.
Yeah, but that's just a constraint here, right? It just tells you that you don't want to receive invalid blocks. So there are these two things. If you have a block response, there is something which is telling you whether this block is good or not. I'm just using this word, okay? not valid or some corrupt. Let's say it's corrupt or not.
Mhm.
And there is another one if the reactor has processed the block, which is telling you whether it's valid from the validation point of view.
Okay, but Igor, then who sets? Because when we start, we initialize this array of blocks with -1,
Mm-hmm.
right? And then who said? Oh, that's the event. Sorry.
That's an event, right?
The
So
event is not the actual. Okay.
yeah, so the reactor can actually produce you any block response event from any peer for any height
Sorry.
for any block. Okay.
Mhm.
So valid here maybe it's just a name that doesn't reflect the nature of this process. But I don't remember, was it actually?
No, but I don't understand it. But it tells the reactor says that the block is valid, no?
No,
Yeah,
That the
I-
block is
kinds
not
of valid. No, there are two kinds of being valid. Okay, so there are two events. One is telling you that you have received a block from the peer, from a peer, right? And somehow there is this flag that is telling you whether it's valid or not. But then the reactor is processing this block here, and it will tell you whether actually this block is, what's the right word? Valid, I guess, right?
You just talk about different levels of
Yeah.
validation. Like one is that block could be semantically valid in a sense that it has the right fields, signature. If it has signature, is fine, whatever. But then it's not for the right height, and it hasn't come from the right peer, for example. And then from the protocol point of view, this is not considered as something positive or good, and that's why we generate error in that case as an event and say this is something bad. But I guess that it makes sense to have this line 238 where from the peer we receive message on block response that the block itself could be invalid in a sense, that it could be wrong, just it could be crap. And that we might want to model this because in this case, then I don't know, we would remove the peer.
Yeah, maybe you should really think about, naming this field just differently, like corrupted.
Well formed or something, no?
Yeah.
Yeah, well formed, yeah. Because, I see a confusion right now. Yeah. Good. So since we started to get into the details, maybe we should look at how the FSM looks like, right? So you have 4 different actions here, one per FSM state, which are telling you what you're going to do in each of these states, right? So that's how I wrote it. We could write it differently. I could have written differently, but that's how I did it. So, for instance, in init, you have these choices, right? If you're in the state init and you receive start FSM, you update your state to wait for peer, and you issue the status request, send status request to the reactor, okay? Otherwise, you just do nothing, right? To produce.
What's the difference between using if-thens and using disjunctions?
There is no big difference. Actually, internally, TLC would treat a disjunction as even else.
Okay.
If you write this, TLC will turn it into that. Okay. But mathematically speaking, of course, it's a disjunction. But, yeah. There is no big difference here.
Cool.
And the same applies to conjunctions. Also, TLC actually understands it as a short circuit, like in C. Right? But sometimes it's just more, it's kind of easier to write an if than else. Sometimes it's easier to write a conjunction or a disjunction. Okay?
Yeah.
Then in wait for peer, you have like 3 choices. You can get a status response, you can stop, or you do nothing. That's just kind of a general definition that tells you don't change anything if you receive something except these guys. So if you receive a status response, you update your peer, right? The one who has sent you the response. And if you have at least one peer now, you go to wait for block, otherwise you remain in the same state. Okay? So maybe it's interesting how you update your peer, right? That's complicated. So here you look if you already received a message from this peer. If yes, then you check its height. If its height too small, you just ignore this guy. If its height is large enough, you update your block pool, right? You add this peer into the set of peers. Right here, I would define these new peers and update the record field here. Then you compute the new array or new function of peer heights, which is telling me that for this peer, now I have height equal to the parameter height. And then I find the maximal height among all the peers I know. Okay? Then the pool is updated with these 3 new fields. Are we good?
Yeah.
That's a bit.
Oh, yeah, this is just, I think we need always, when we are modifying the some variable, we need to say that like keep the old values and just modify the new one. I guess this is just the TLA.
Yes. Yeah, that's good. Because this one is a function, right? You don't update only one element of the function, you update the whole function. And the new function will look like this. It will be exactly like peer heights, except for this value, which will be equal to height for peer ID. So it's a weird syntax, not like you would write in a programming language, but essentially it's like assigning a value to one element of the array, of an array here, right?
Yeah.
So
in this case, there are no really like these transitions, so we don't see this ampersand sign, because this is really like the update peer is just operator. It's like it can be seen as just a function, or it is a function.
This is a function. This is a function.
The update peer. I mean the whole update peer logic. Like what starts with the
yeah, you can see it as a macro. Okay.
It's a macro. Okay.
It's essentially a macro. It's called an operator definition, but all of these guys can be expanded by macro substitution, essentially.
Okay.
Right. So it's just a huge formula that is going to be replace this operator in case you call it with these arguments.
Yeah. One thing which is a bit confusing to me is the fact that you can modify the state by just defining this macro as we see here, and also using this ampersand when you define the kind of transition. So
what do you mean? This I don't get.
Yeah, so normally when we want to say like this is the old state, this is the new state, we use this, I guess it's called ampersand sign.
Prime, you mean prime, right?
Prime, yeah, you're right. It's prime. Yeah. But like it seems we can also update the state of some variable without using prime.
No. I kind of tried to write it in a functional way without going to primes too much, okay? But in the end, if you update the peer, you see, it propagates to the primed variable. See?
Okay.
So I'm just trying to write these definitions as if they were like in a functional language, because it makes things easier. If
this line is saying the block pool will be updated according to this rule, and then this rule.
It's just saying that update peer will compute the new block pool, and block pool prime will be equal to.
Okay.
Yeah.
Okay.
I mean, I find it much easier to think about the specs when you do it like this, because in TLA you can do updates in any place, like like if you had a functional language where you could do assignments in any place. And well, it's not nice, it's very hard to read the specs. But good point, good point. So we receive this status response, right? We update the peer and we update the block pool, okay? And there is a lot of similar logic like this. So this make requests is a bit complicated because you have to understand for which blocks you haven't made requests so far. You have to understand how many of them you have. And here I say cardinality, which means the size of the set. Then you compute the new request height. Here we had a lot of argument, I guess, because it's a complicated formula, right? And then you compute the set of new heights for which you are going to make requests. You compute the new blocks by saying either I have already made the request here, or if I didn't, and if I want to make a request for this height, I just choose a peer from the set of peers I know, so that this peer has height which is at least h. Okay? So this is a very interesting construct. In the implementation, you will actually choose a peer randomly, as far as I remember. Or you kind of try to randomize this. And here you just say, I pick one of these guys. I don't know how, but I will do it. Okay? This is something interesting that TLA has.
But then again, TLC will explore all options.
For choose, not.
Okay.
So for choose, it will. The rule is that if you give the same set here, essentially, if this set is the same, then this set. If this set is the same, you should get the same value. It's like it's a black box algorithm. You don't know how it works. You don't know its implementation, but it's an algorithm. Whenever you give...
The problem also is V1 and even V0 doesn't have a deterministic algorithm to pick up a peer for a given height. And it's pretty much the same in the Go version, right? We do a range over the peers and we pick up the first one that we find.
Yeah, but the range, as far as I understand, you told me that range is kind of randomized, right?
Yes, exactly. That's why I'm saying it's not, even if we would want to do something like in the Go implementation, at this point, we couldn't do it because we don't have the implementation picks randomly up here.
Okay, we could introduce non-determinism here.
Yes, exactly. So,
but that will explode things.
No, but I think the solution is to have a proper selection in the Go implementation and simulate that here, right?
Yes, if you can do that, yes. Yes.
Yeah, we can do it. So that's something we still have to do.
Yeah. Okay, so I mean, it's kind of by far the most complicated thing in this spec, I guess, how you pick new blocks and how you construct them. And then you say, I made a block request to the reactor, and I make all these requests for all these heights. Okay? So that's a set of records. This record, each of these records has two fields, peer ID and height. The peer ID of this guy is equal to the one we have selected here. And the height is just something that you got from the set of heights. Okay. So I guess, yeah, I mean, we can look further into these events, into the processing part, or we can run the model checker, whatever you like.
Yeah, probably it would be cool to see what we can check with model checker.
Exactly, because I guess it's too much to digest here.
No, but I think that my impression is that the level of details we have here is not significantly more than what we have even with English spec. It's just more precise, much more precise. But if you try with English spec also to cover all important cases, you would somehow need to mention what is happening in this case, what is happening in that case. You know, and so right now we were doing it either with some kind of pseudocode or English wording, but in case you really want to be precise, it can be quite also lengthy, the spec itself.
Yeah, I mean this protocol is quite complex, as I understood later. I thought it's quite simple. Yeah.
In that sense, I don't think that for me this is not. I mean, it takes some time to get used to just what it means and the syntax, but my initial feeling is that it's not the effort is not significantly higher compared to what we have there. It just forces us to say what it means. You know, like what to whom, what would happen when I get this message? Like what is the peer I will choose? What is the message I will send? How the message should look like? We need to have answer for this question. And so here the additional benefit is what we'll just see now, that we can do a bit more than it compared to the English or pseudocode based spec.
Yeah. So there are a couple of specs that actually they're just thrown, right? Because we wanted to see what's going on when we just check some properties. For instance, here's a spec. Here's a property which is telling us whenever we finish, the height of the block pool is smaller than the maximal peer height, right? So you probably believe it's wrong, and it is. But let's see if the model checker can convince us.
So this means that we terminated before downloading all available blocks.
Yes. Okay, just check this. And here I'm not checking invariants because this is a temporal property. I could have written differently, but this is a temporal property. So I'll put it under the properties. If it was invariant, I would put it here. Tick the safety. And by default, TLC would always check for deadlocks. You can also tell it.
Sorry, can you clarify the difference again between invariants and properties?
So an invariant is something that should hold in every reachable state. And it's much easier to check because you just compute the reachable states. And for each reachable state, you actually evaluate this formula, right? For instance, this guy is an invariant. It's just a formula over a state, which tells you that if you reach the height, block pool height, then whatever lies before should have been processed, right? Just compute all states and check whether this property holds true or not. This guy could be written as an invariant, but I was probably lazy. I wrote it as a temporal property, which says that for every state in an execution, this should hold true.
So how is that different from an invariant if you're saying in every state?
I mean, this one can be written as an invariant. This is an invariant, actually, this guy. Yeah. This guy is telling you, explore all states of an execution. This one, you cannot write as an invariant. I mean, you can, but it's more complicated. You can.
Does TLC make a difference whether you write an invariant or a property like never finish at max?
I guess TLC is smart enough to check the invariant instead. I would expect it. So for this guy, I guess it would just check the invariant. For this one, it's more complex. This one is telling you that if for all states in your execution, you don't have an event that has type stop FSM, then for every state in your execution, you have this property that whenever you finished, you have this height equal to the max per height. Okay? Still can check it with invariant. It just needs a bit more additional work. You need additional variables here. Okay? But invariants are usually much easier to check. That's kind of the main message. Are we good?
Sure.
So let's check the invariant. I just added this, added the values for all the constants I had. So I have 2 requests per the event where you issue requests. I have 3 peers. I have 3 peer IDs, 0, 1, and 2, and the ultimate height is 3. Very simple, right? But this one is good enough to find the counterexample. So remember, we wanted to check this property that whenever you are finished, the block pool height is smaller than the max peer height. Here's the counterexample to this property. What it's telling us, we start this state, we start at height 2, no peers. We already processed block for the height 1 because we started with height 2. We don't know peer heights. And the next request height is going to be 2. Max peer height equals 0, and yeah, received blocks 0 and 1 so far. Then you send status request, right? Because you started, then the reactor is telling you that you, let's see what happens here. So the reactor is actually making a turn, and then it sends a status request, and then FSM stops, right? It's a very silly counterexample. But
so reactor starts, FSM sends status request, and then reactor stop FSM, and that's it.
Yeah. So just disproves that your height should be always smaller than the max peer height.
So if reactor can send stop FSM event at any point in time, then you might terminate before max peer.
It's a timeout, right?
Yeah.
So you start, you try to get statuses, you get nothing, you get a timeout. That's it.
Yeah.
Yeah. I mean, it's kind of a stupid example, but that's an example. Then the next property, which is telling you if I never get the timeout, right? If I never stop FSM, and if I finish, then I should for sure have this, right?
Mm-hmm.
Then my height should be equal to max peer height. You believe that?
Yeah.
I also believe that, but it's wrong. So let's see. Maybe it's not. Maybe you have changed the spec. Then.
Yeah. One thing which might be interesting to see if it's possible to model is faulty processes. So
we have that. We have that.
Ah, okay, cool.
No, I mean, what it means to have faulty processes. The reactor is just producing events, right?
Yeah, but like exactly, like it gets event from the faulty processes.
Yeah.
Which are sort of not respecting the protocol. So, for example, the faulty process might send you the messages for the heights which are above ultimate heights, for example, in your model, or
still doesn't work, you see. So this one's pretty long. Okay, so we send a status request. The reactor tells us to, yeah, it sends a status request, then the FSM is receiving a status response from peer number 2 with the height number 2, yeah, with the height equal 2. It updates the block pool. That's peer number 2 here. Then you get a block response, but you see now the block is corrupted. You see? So it's corrupted. Then you kick out this peer from the set of your friends, right? You have no friends now. You send peer error. You get another status response from peer number 1 with height 2. You add this guy, you get a block response. This guy is good. The block is not corrupt. But then there is a condition that, let's see, why?
I think we haven't asked for blocks and also.
Exactly. So you receive a block response with a perfect block, but from a peer who we didn't ask to send a block, right? So you send a peer error. You don't like it. Then you get a block response from peer number 1 for height equal 3. I'm not sure it's good. Yeah. So you again kick this guy out because it has sent you a block for the height you didn't ask for, I guess, right?
Yeah.
And then you send a peer error. Then you get a status response again, peer number 0, height number 3. You wait for block. Now you make requests, you know. The first time you actually make requests and you send 2 requests for peer number 0, for the height 2 and height 3. You get a block response. It's a good block, but from, yeah, it's even from a good peer, I guess. Yeah, it's from a good peer. Then you do nothing. Then you get a block response for height number 3, so it's all good. Then you get a processed block event with an error.
Yeah.
Right? So now the reactor verified the block and it's not happy. It sends an error, you remove the peer, you get a block response, good block, invalid peer. And then since you have no peers, you switch to consensus.
Yeah. But it's not so silly, the scenario.
No,
And
this one is not silly. This one is not.
it's actually answer also to my question, can you have the faulty behavior? Because this is exactly what we have here.
Yeah, you know, Žarko, it's so hard to find one that doesn't have faulty behavior. Like, debug this, and sometimes there are loops like with the diameter of 30 and 40, and then you look through it and it's like, oh my god, only almost 90% are error messages.
Yeah, so the challenge is to somehow constrain check for a good case.
Yeah, exactly. That's why Igor came up with that good termination, trying to limit the number of timeouts and errors. But even there are so many.
So,
like if you think about the, like in general, the distributed protocol, what we are doing there, if you want to prove some liveness properties, we always constrain the space really a lot.
yes.
We say like everything is synchronous, there are no message loss. Sometimes even you can assume the message is coming in order. There are no faulty processes. No one is allowed to crash. No one is allowed to send you any garbage. And
Very good, Žarko. That's what we have here. It's called good termination, right? So that's the first thing we try to do for liveness. So we say, you know, don't stop FSM. You don't have this global timeout. You don't have failures nor timeouts. So you don't remove peers, right? You don't get bad block responses. Whenever you process a block, it's always good, right? and you don't have, you know, an infinite chain of status responses, block responses, process block events, you know, all these things. You know, there is also an option that the reactor is always feeding you with these events you don't care about in the end, right? Say, for instance, you can always get status responses, yeah, without any progress. So we eliminate all of this, say that from some point on, you don't have these events anymore. You can get them, but only for a finite period of time. And then you say that eventually I will finish, and my height will be at least as large as a max peer height. Okay, that's a good termination. So this one does hold.
Sorry, can we before we move on to that one?
Yeah.
Can we talk about why this failed? Is there a bug somewhere, or we're just wrong about the?
They're just wrong. I mean, this can happen because you.
But this means you can switch to consensus before it gets to the max peer height, right?
Yes, because you're receiving blocks, and these guys are actually faulty, perhaps, right? They're sending you wrong blocks, and in the end, you just switch it by timeout, essentially.
But do we want to fix that, like, so that we don't?
No, it's not like there is no problem with the protocol here. It's just our definition of termination is not correct. So I think this is, so you as done here, the termination need to be constrained to the case where we don't have failures, and then.
No, but why should we ever switch to consensus if we're not fully caught up?
There are no peers. All peers are faulty.
Yeah, they're all gone. So they fed you a bit of bad blocks, and then you kick them out, and that's it.
So this
You don't
is
reconnect to them or anything.
If there are no peers, like all peers you talk to are bad, then you wait some time out.
Yeah.
So you don't immediately switch, and then no one shows up. What you can do, like the best you can do.
Yeah, you're right.
Yeah,
Cool.
here actually we didn't switch by timeout. I guess here we just switched.
What does the red indicate? Like, why are
That's
some
what has changed.
red?
That's what has changed between the states, you know.
I see.
It's actually quite
I think this is a weird scenario. We talked about this. I think the way this ran, I don't know, Igor, if I'm right, but we started starting height is 2, right?
Yeah.
And then max peer height is 3.
Yeah, the ultimate height is 3, right? That's actually a very good scenario. That's true. So essentially, you will never receive a block. One more block, so you can validate this one, right?
Yeah, can you go back to what we ran, property definition for this one?
This one?
Yeah.
Yeah, you never have a timeout here. Actually, you didn't quit by timeout. You realize that you have no peers anymore, right? That's how you quit.
But you allow bad peers. You allow peers to send you messages you haven't asked for.
Yes. You have faults, lots of faults.
And if you have faults, then if you are surrounded by faulty peer, it might happen that it's partially, it's also maybe the protocol itself could be improved, because if we don't have the max peer height, it might look a bit different, because in this case, the block pool max peer height has been updated with the values of faulty peers, but when you kick them out, you haven't removed, you haven't decreased the value.
No, you did decrease.
You did decrease. Okay.
Yes.
Yeah,
Okay.
that's why we switched to consensus there, because if we
You're right.
wait for some peers, we get some peers, we get PAGA, and we forget a peer. So that's the way the code is written, and it's not the best thing. But the trigger in this case is once if you remove all your peer, you've synced some blocks, and then you remove peers and your new max is smaller than your current height, then we say switch to consensus. We don't wait.
Yeah, here you don't have any timeout. You just terminate by this condition. Which one is block response, right?
But there's, yeah. Yeah, I think there's a problem, I think we should keep this in mind and look at the code again, because if I remember correctly, if we get a block response event, and then if we send a peer error, we should have removed that peer, and I don't think we had another peer there. And we should have moved to wait for peer, and there we have a timeout to wait for a taller peer, so we don't abruptly switch to consensus. But
oh, actually, it happens here, right? We processed this block, which was invalid.
right.
And since we have reached the maximal height here.
Yeah, but there we should check that in the code. I think we check if we don't have peers, we go to wait for more peers for taller peers, just in case, right? We are just at the start of the process, and we get this one peer that tells us this, and then we.
Yeah, we should check for this condition in this section.
Yeah, so here we have to add, because that's.
Yeah.
We check number of peers. It's.
Yeah. Good. So shall we continue the good implementation? A good termination?
Yes.
So yeah, here you have a number of constraints, right? As Jarko is saying, that's exactly what you want to do. Want to see whether it works at all. And this actually, it should work. I checked it yesterday, so it should work. So it will compute like for 2 minutes, maybe. You can look at it again, right? So you should finish, and your height should be at least as large as max peer height.
Wow, that's a lot of states.
No, this is not a lot. No, that's just the beginning.
You're like little baby.
Actually, I mean, right? It's not a lot, no, really. 2 million, nothing. So let's see, it's almost done. Yeah, so now it's done. And this one holds true, but it's kind of strange, right? Because we have so many constraints here. Maybe the protocol could be much simpler if we had all these constraints in mind. Then if you remove these constraints and you just say that you should infinitely often issue this block request seeker, right? That you should request for new blocks as soon as you can. This doesn't hold true, right? So in presence of faults, you have problems.
I should ask, what was that fingerprint collision probability that came up in the model checking results?
So actually, what TLC does, it's an explicit state model check, right? And it enumerates states, but instead of storing all these states in a disk, on a disk or in memory, it actually stores hashes of these states.
Oh, I see. Okay.
There is a small, yeah, there is a small probability of that you actually confuse two states. So, you know, it's almost correct. With a small probability, it can be wrong. And then it gives you this probability.
Okay, great.
Yeah. So this false termination is just wrong, and the counterexample is super short, right? You get one block response with an invalid block, and that's it. You have no peers. You switch. No, wait. You never terminate, right? You keep iterating here, starting with this state. Do you see that? So you get an infinite chain of block responses. So you get this, you go back to state number 3. A simple way not to terminate if you don't have additional constraints. Okay.
So what does it mean, that the reactor gives you the same block infinitely often, or?
Yes, but you can also imagine that, yeah, in this case, yes, but you can also imagine you have a lot of peer IDs, right? So the reason why it happens here, this cannot happen in reality because you have a timeout, right? And here, since TLA, I mean, it doesn't have a notion of a timeout like this, you have to add additional constraints that will tell you that eventually a timeout will hit, okay? So that's how you probably try to prove termination in the first try, but that's not how you should do it. And then we like scratched our heads for a long time, and we wrote this termination property, which tells you that this protocol can terminate even in the presence of faults if some conditions hold true. Okay? That's a very complex property somehow. What it tells you is that if you start with a height that is smaller than the ultimate height, and you issue block requests, and you keep increasing your height until you have reached the ultimate height. Or if you cannot do that infinitely often, then you should stop the FSM.
Do you want to say a little bit about fairness?
Yes, it's fairness property. So instead of having timers here, we say that some things should happen infinitely often. For instance, here, if you can issue a block request ticker, you should do that. Or infinitely often, you should increase your height unless you have reached the ceiling. And if you cannot infinitely often increase your height until you have reached the ceiling, then you should stop the machine. Okay? So that's how you restrict your execution space to the interesting scenarios. In this case, you always terminate, either by reaching the ultimate height or by stopping the FSM. Looks complicated.
Very much so. What is all the like WF and SF and the double brackets or the double angle brackets?
So that's weak fairness. That's a condition which is telling you that this action, if it's enabled from some point on, it should be taken. You know, whenever it's enabled continuously, it should be taken. And this one is strong fairness. That's why you have SF, telling you that if this action is enabled infinitely often in an execution, it should be taken infinitely often. So that's how you kind of, instead of reasoning about precise timers, that's how you reason about events, you know, in asynchronous executions. That's a way to express that some events should happen in your execution. Okay?
Okay.
So this one holds true, but now you see that we have this very interesting condition. So it took us some time to understand, I guess, right, Anke? I mean, not some time, but like several hours, maybe. So if you start your fast sync with a height which is equal to the ultimate height, the only way, no, that is not true. You actually never increase your height, right? Because you cannot validate the blocks. So essentially, yeah, here it's captured here. If you start with the ultimate height, if you don't have the global timeout, and if you don't receive any updates from your peers, you will never finish. Okay?
But ultimate height is an artifact of modeling, right?
Yes, but you can imagine that you never receive an update that is telling you that somebody has a height higher than this ultimate height.
Yeah, but ultimate height, it's not represented in any variables of the protocol. It's some
that's some
view of the system.
Yeah, it pretty much simulates the case where you are at the highest height. So you start the fasting at height 100. Nobody else, no other peer is at a higher height than 100. So it's a way to express this condition. So any peers that come up and would send status updates will be less than or equal to your height.
And the interesting thing, if you don't receive any further updates, the only way you can terminate is by timeout. That's somehow the interesting message here. Okay.
Cool.
So yeah, it looks like we actually managed to understand what kind of termination properties this protocol has.
Wow.
They're not simple.
Very cool work. It's amazing work, guys.
Yeah.
Yeah, thanks. I can imagine it's like really a lot of TLA code to read. That's a bit of a problem.
There's a lot of what?
A lot of code here, right? I mean, usually you'd imagine you have some piece of pseudocode, which is much smaller.
Yeah, but this is not like you're only here the module, like almost all business rules. So this is not like the, I don't know, consensus protocol where you have 3 business rules and that's it.
I think the complicated stuff is what you have here, the cursor on the temporal logic property and the fairness stuff. This is that becomes very intricate.
Oh yes.
Yeah, this was also for me the surprise. You know, up to here everything seems okay. You learn the language, how to express all the, you know, macros and functions and whatever they are. But then here it requires a lot of thought because you cannot just do.
But it is complicated, right? It's not so clear, not so obvious what termination properties this one has.
Yeah, it's not like it's inherent. It's not like that it's TLA fault.
Exactly.
When I was thinking about this protocol first time, I was not able to define the termination property. I was thinking along those lines. I mean, it's kind of very interesting that you kind of came up to more or less the same things, which kind of I was intuitively also having. That you need to constrain all those stuff because this is not something kind of done before. The problem is not well phrased like maybe consensus or some reliable broadcast, so you can just use the properties and try to check them. So here you really need to come up with a definition, and then the model setup is very tricky because you have faulty processes, you have peers, you don't know really. It's a lot of unknowns. And
that's why, I mean, it took us some time to come up with this properties actually, because it's, wow.
So this weak fairness turn, is this somehow from the modeling? I have the impression that anyhow the model says that you have to sort of in every step change the...
No, that comes to the features of TLA, okay? Because in TLA, essentially, you can always extend the execution with the stuttering steps where you do nothing. And you can watch video number, I don't know, 10, where Les Lampert explains why he wants it. So
stuttering is always, even if it writes like, if I read this, it looks pretty clear that you have no stuttering, right?
Yeah. even if you write it like this, it will still add a stuttering step in an infinite execution.
I'm totally on the side of Leslie, but it's weird that it's written like that. Okay, so stuttering is super important because for the refinement, everything, this is the point. But if you write it like this and it's still there, that's weird.
Well, I mean, that's called communication. How it's called? He had this property of machines like closure or something like that. So he thought a lot about it, and then he restricted the language to work like this. But it's really like you always have to think about fairness. So yeah, that's a very nice protocol with non-trivial properties, I can say.
And so in the what guarantee do we have that stop SFM isn't going to happen like too early?
In this model, well, I mean, this constraint is telling you that you should look at all executions where say in this case, even don't have to have a stop FSM. If you have, an infinite chain of these events where you increase the height or you have reached the maximum, the ultimate height, then you even don't have to stop FSM, right? So this whole thing is a constraint on the execution space. And there are two kinds of executions where you eventually stop FSM or you keep hitting these states where you increase or you have reached the maximum. So in this scenario, when you have hit the maximum, you will terminate without having this event.
But couldn't aren't there trivial executions where stop FSM, like how do we know that stop FSM is only going to happen like legitimately? Like shouldn't we also have some constraint that says like, stop FSM will only happen if we also have like no peers or all of our peers are below the height?
I mean, that's a good question, right? So you have a disjunction, right?
Yeah.
And if you have executions where this property holds true, you don't have to stop it. You can consider executions where it doesn't stop.
Mm-hmm.
And it's a fair question whether this is a good constraint, right? But that looks like the reasonable one. If you keep increasing your height or you have reached the maximal one, then it's okay, right?
Mm-hmm.
So you don't think in terms of how you do interactions. You just think in terms of what are the minimal constraints that you can apply to executions, so you don't need to stop FSM.
But I think the model checker will try also scenarios like you have in mind. Right?
Yes, because they will
try, it will advance the block height for a while, and then it will get a simulation of a timeout with stop FSM.
Yeah, because if this condition doesn't hold true, right? If you stopped increasing your height and you haven't reached the ultimate height, the only way you have to get out of it is by stopping the machine, right? I mean, it really requires a lot of reason at the temporal level when you talk about executions and what happens infinitely often, what happens from some point on, what happens, eventually.
But does this guarantee that if we stop FSM, it means the height wasn't increasing?
No. You can stop FSM in other cases, right?
But that's what I'm saying. How do we know that the stop FSM happened where we wanted it to and not like just trivially?
Well, there are always these executions where stop FSM happens trivially. You consider these ones plus the ones where stop FSM never happens. So you really have to think about all possible executions. You see what I mean?
But doesn't that kind of trivialize this termination condition?
No, because in this case, you don't have to stop FSM. When you infinitely often have this property, right? You don't have to stop FSM, and it actually includes the executions where you never have the event which is called stop FSM.
Mm-hmm.
So it's really like, it's a union of two execution spaces. But fairness is very hard to think about, because it's very easy to kill interesting executions by writing these constraints.
Actually, somehow I think we thought in the beginning differently. You want to say if you don't stop FSM, you increase your height infinitely often, no?
But this can happen, right?
No, this cannot, but yeah.
Yeah.
But this is sort of the idea. If you keep on going.
But still, how do we make sure that stop FSM is only happening in legitimate cases?
Then you have to be more precise about the reactor, no?
Yes. I mean, but imagine you have this timeout, right? It can happen whenever you like, essentially, right? What are the legitimate cases you're talking about here?
Yeah, I guess it means that, there was either we have no peers or we had the timeout. How do we ensure that stop FSM is only happening in those conditions in this property?
Well, you can kind of restrict. You can.
But it's a property on the reactor, no? It's not a property on the FSM.
I mean, you can fairly restrict this condition, right? But what I'm saying is that if you don't have this increase in, if you don't have this condition, essentially, what do you do? The only way you should stop at some point, no?
No, but if I understand, so for me, this model here, it checks properties of the SFM under the assumption that the reactor is somewhat nicely behaved.
Yes.
And Ethan's question is, how do we check that the reactor is nicely behaved?
Yeah, exactly.
Oh, I see.
But then you would need a model of the reactor.
Model for that, right?
Yeah. Yes. I see what you mean now. Yeah, we have this reactor. You can write additional properties on the reactor.
Right.
What it's supposed to do. But I mean, now if you look at the actions, you can issue stop FSM whenever you like. That's why you have to write additional constraints that you don't do it all the time.
Right.
That's why you need this guy. Otherwise, it would be trivial. You just stop FSM and that's it.
Yeah, the problem is with the reactor and outside, whatever is outside FSM that's left to be modeled, it involves a lot of timers. And
Right.
we were wondering, how would we simulate this properly? And what does it mean really from a model point of view? Because we don't really, probably to check that we started a timer and to simulate a stop, right? To make sure we start the timers. That's one thing we should do. So this is something we don't do right now. For example, I don't think we have start timer event from the FSM to the reactor.
No.
So we could add that.
Yeah. But in the end, we actually got rid of most of the timers, right? We just have one single timeout in the whole model here. That's stop FSM.
So the peer timeouts we simulate with the peer remove events, we got rid of those. All the state timeouts we got rid of, and we said we are going to, in an implementation, we could have what Igor proposed to have a monitor module that deals with all the failures and timeouts and everything.
Yeah, that was one idea. Yeah, when we looked at this spec, right? it's pretty large, and it makes sense to decouple, failure handling from the actual synchronization.
I think in general, this is something we.
Sorry, go ahead.
I just mean that I think we discussed also in Berlin this. I think Sean was having a good comments there that whenever possible we'll try to come up with some kind of abstractions in terms of within a protocol itself and the state machine of the protocol, so that it's more easy to understand, what it does, and also from the engineering point of view, that we can have a reasonably sized works, tasks, and that you don't necessarily need to understand the overall protocol to be able to work on a part of it. And I guess from the TLA spec point of view, also being able to scope things smaller, it would be more readable, and maybe also the what TLC is telling us will be also more reasonable and faster, and so.
Yeah, I mean, for this spec, it's quite fast, actually. I mean, it's not so bad because it's a relatively simple spec. You don't have a lot of concurrency here, just have non-terminal. But I guess really one message that we have here, that the few timers you have, the better. That's the thing you're struggling with, right?
Well, yeah, but the thing is, even we hide the timers, but somehow we have to assimilate a timeout with an event anyway. I mean, we have to send an event to the model.
Yes.
That it's, maybe we don't call it timeout event, we call it peer remove event, but that's a result of a timer that has expired. And the question is, we take out, so we make the model simpler, but in the same time, now to Ethan's point, how do you check that these events are actually, that we actually start the timers, and the timer will fire, and that we cover this side of, and I think it should be in a different model, right? It's for the reactor or a different, it's going to be not part of this, because we had it part of this, and it became so bloated and almost impossible to follow. And then we removed all of them. And
yeah, well, that's a good point. You can also make a model of the reactor and show that it's issuing these events periodically, as you would expect from a timer, right? But I mean, in general, when you have timers, you have these timeout values of like 10 milliseconds, 20 milliseconds. I don't know where they come from. I guess the only role of them is just to make sure you have kind of infinite behavior, that they occur infinitely often. Of course, there is something about the order in which they appear, but
Should we try to wrap up this?
Yeah, I guess so, yeah.
So, yeah. Well, this was great. Thanks a lot, Igor and Anka, for the work on this and for the presentation. I will stop the recording.
Cool.